Now let's work problem 6.43 from the book. It asks, what will be the final temperature if I take two different beakers of water and pour them together and mix them together? And of course the trick is that these beakers are different amounts of water at different initial temperatures. In beaker number 1, I've got 155 milliliters of water at 26 degrees. And I'm going to mix that with 75 milliliters of water at an initial temperature of 85 degrees. So this is the initial states before mixing. We're going to pour the two water samples together. We want to know what would the final volume of, or what would the final temperature of water be after mixing. Okay, so this is kind of a fun problem because it ups the difficulty level a little bit. Now we're also told that we should assume that no heat is lost to the surroundings and no heat can be transferred either to or from the containers. Okay, that would also be an important, practically if you were to actually do this experiment in lab, that term could be very important. Okay, but we're going to assume that that's not important here, and we just want to consider the water, which does simplify things a little bit for us. Well, what in the world are we going to do with this problem? Okay, well, let's think about it a little bit about probably what's going to happen. We've got some room temperature water, about 155 milliliters of it. Room temperature is usually about 25 degrees, okay? So that's just sitting out on the bench top. And then this water is 85 degrees Celsius. That's almost boiling, right? 100 degrees boiling. So this is pretty warm. So if I take this 75 milliliters and I mix it with this cooler sample, the final temperature is probably going to be somewhere between the two. I mean, this water is probably going to heat this up a little bit. This water is going to cool down. So the final temperature is probably going to be somewhere in between. But if I'm going to figure out exactly what the final temperature is, I'm going to need some quantitative framework through which to work, okay? And the quantitative framework that we can use is actually going to be sort of deceptively simple here, okay? There's this law of conservation of energy, right? Energy can't be destroyed or created, blah, 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 right? And I don't mean to make that sound like a silly statement, because that's really what we're going to use here as it applies to heat, okay? The heat that this warm sample contains, it can't go anywhere except be transferred to the molecules in this sample and heat them up a little bit, okay? So the heat energy has to be conserved. And the cool thing about that, then, is what I can do is write a statement such as the one here. Q lost, and I'm going to multiply that by -1 or change the sign, is equal to Q gained. And what I mean by that is that the heat energy that's going to be lost when this water sample is cooled has to equal the heat energy which is gained by this water. The heat energy has to go somewhere. The only place it can go is warming up this water. So we can write this statement. Now once we write that statement and establish that as truth, we're really off running now. Because in previous problems, we learned all about how to calculate heats associated with warming or cooling objects, right? So could I compute how much heat is going to be gained by this beaker? I think I can, right? All I need to do that is my heat capacity C. I multiply that by my mass, M, and then my delta T for that water sample. Now, do I know these variables? I think I do, to a certain extent. For instance, I'm dealing with water, and we know now, hopefully, that the specific heat of water is 4.184 joules per gram per degree Celsius. So that's one number, that's my C. Do I know the mass of that water that's going to be warmed? Well, let's see, what do I know about it? It's 155 milliliters, that's a volume, but I also know the density of water is just 1 gram per milliliter. So 155 milliliters is essentially 155 grams. So that's what I'm going to be heating up. Now I also need a delta T, which is my temperature change. That's a little bit of a problem because I don't know how much the temperature is going to change. I mean, I know it starts off at 26, but I don't know where it's going to end up at. I mean, if I knew where it ended up at, I could put a number there and that'd be good, but I don't know what that is, right? So what do? Well, I remember that in chemistry, whenever you're going to compute change in something, it's always final minus initial. So I can basically expand this delta T term as T sub F, the final temperature, minus 26 degrees. Because 26 is the initial. It's just final minus initial. And then I've got only one unknown over there, which is my desired answer here. That's the final temperature. That's what I want to know. Now what about this other side? Can I compute how much heat energy is going to be lost by the warm water? I can probably make some progress in that direction at least. Same equation, Cm delta T. Don't forget we need that negative sign. Let's just flip the sign, okay? Now, I'm still dealing with water. So 4.184 joules per gram per degree Celsius is still the specific heat. I need to multiply that by the mass of the water. Now it looks like I've got 75 milliliters of the hot water. We're going to assume that the density of it is still 1 gram. There are different temperatures which would make their densities a little bit different, but for our purposes here in this problem, we're going to assume it's 1 gram per milliliter, okay? So 75 grams, 75 milliliters, and then I got this delta T term again, right? Well again, can I write T final minus T initial, where T initial was 85 degrees? So that mathematical statement also works, okay? Now here's the trick. This TF, the final temperature, and this TF, are they the same number? They are, right? Because what's going to happen when I mix these two water samples, they're going to reach some intermediate temperature and everything is going to end up at the same temperature. So the final temperature for this term, for the heat lost from the warm sample, the final temperature is going to be the same as the final temperature of the stuff that warms up. Okay? So that's the beauty of this. We can write one equation with only one unknown, this T sub F, and then we can go about solving it. Okay? So the first thing I'm going to do is I'm going to multiply these numbers together to sort of make some quantitative progress here. So if I do that, I get negative 313.8, and then keep my T sub F minus 85, my initial, okay? And I'm going to set that equal to 648.52. That's just doing the multiplication of these guys, okay? So that's still going to be T sub F minus 26 degrees. All right, so I made a little bit of progress there, but I still got this term in parentheses that I'd like to clean up. So now I'm going to distribute the numbers outside the parentheses to make negative 313.8 T sub F plus 313.8 times 85, both being negative, so that turns into a positive 26,673. And that's going to equal 648.52 times T sub F minus 16,861.52 for the multiplication of 26 times 648.52. All right, so we're just cleaning up the equations here. Now what we can do is combine like terms, okay? And what I like to do to make the signs both work out positive on both sides is I'm going to keep my TF term over on the right. And to do that, I'm going to basically move this one over there. okay? So I'm going to keep the 648.52 there, move this one over there, flip the sign into a positive number, and that results in 962.32 times TF still, right? That's our unknown variable. And then likewise, I'm going to keep this 26,673 right where it's at. But this one, which is just a number, I'm going to move over here, combine it with this number, flipping the sign in the process. That results in 43,534.52. Okay, so I've reduced the equation down to this. Now it's just algebra, right? T sub f then must equal 43,534.52 divided by 962.32. And if you do the math on that, you get 45.23 degrees Celsius as your final temperature. So we might say 45 degrees, 45.2 degrees, right? So the cool thing about this is we've figured out what the final temperature of the mixture of water would be if we mixed together two different water samples. It used some of our fundamental core concepts that we've been learning about in sample problems in this chapter, which include the computation of heat flows as an object warms or cools. That's a major problem type from chapter 6 here, okay? The calculation of these Q terms using equations that look like this. It's a major deal for this chapter, okay? But this went up the difficulty because it didn't tell us what the final temperature was. We had to kind of figure it out through our reasoning. And the key idea there was this equation, is that the heat lost by the hot object has to be equal to the heat gained by the cold object. The heat can't be lost, can't go to the surroundings because we were told that that's the case. So those two things have to be equal, and that was kind of the key link that we had to make. And then from there, it just becomes kind of a algebra problem, okay? All right, so it's a fun little problem.